Okay, so obviously in maths, our favorite thing to do is to add lots of things together. So along with finding the sum to n terms of an arithmetic sequence, we're going to find the sum to n terms of a geometric sequence. Okay, it's a bit of a strange, convoluted method of doing this, similar to the arithmetic one, but it gives us a really nice formula. It's a really nice method, but you don't have to memorize the method. You don't need to know where the method comes from. You don't even need to memorize the formula, to be honest, because it's in the formula sheet, okay? But I'm going to show you this nonetheless, okay? So geometric sequence is formed by adding together the terms of a geometric sequence. Did I say sequence? Geometric series? Anyway, terms of a geometric sequence are AR squared, and so on and so forth, okay? We're going to let Sn be the geometric series such that, okay, Sn equals all of them added together, okay? So all the terms in the series added together. Right. By randomly multiplying everything by r, it's going to lead us on to the formula. So just bear with me here, okay? But multiplying everything by r gives Rsn equal to AR plus AR squared all the way up to AR to the power of n. Basically, we're trying to do something so we don't have the AR to the power of n minus 1. It just makes things a little bit more awkward, okay? But it does lead into a nice formula, okay? So by actually subtracting these from each other, again, don't worry too much about all this. This is just going to narrow everything down, because by taking a bunch of things away, then we have less stuff. Okay, so what happens here, if we take Sn or Rsn away from Sn, then we actually just left with a minus AR to the power of n. Okay, you can see here, everything kind of disappears apart from the a and the AR to the power of n. Okay. In which case, Sn minus Rsn equals a minus Arn. Okay, and if we simplify this, because obviously what we're trying to do here at the end of the day is we're trying to find a formula for Sn. So we're going to take out Sn as a common factor here, and we can take out a as a common factor on the right-hand side. Okay, and then we can divide both sides by 1 minus r to give us a formula for Sn in terms of a, r, and n. Okay, which is a nice formula, but as I say, it's given in the formula sheet, so you don't actually need to memorize it. You just need to know that it exists. And if you're trying to find the sum to n terms of a geometric sequence, this is the formula for you. So, yeah, you can rewrite it that way as well. Okay, so you can rewrite it like this. Sometimes that might be useful, but generally, yeah, either or is fine. I can't actually remember which one's in the formula sheet, but yeah, you can rearrange it if you need to. So a is still the first term of the series, r is still the common ratio, and n is still the number of terms, okay? So I'm going to show you a few examples on using that just now. Start with a really basic one. We're just going to find the sum of the first 10 terms of the geometric series, 3 plus 6 plus 12, right? And so on and so forth. Obviously, you could just add all these together, okay? But I think if you're going to be asked this in an exam, it might say using the formula. It would probably just be a more complicated version of these, more similar to the kind of the examples that are going to follow this one. But this is just getting us used to the formula. Okay, so we take that formula from our formula sheet and we plug in everything that we know. So we know the first term is 3. We know that the common, we've got 10 terms, sorry, and then we know the common ratio is 6 divided by 3 or 12 divided by 6. It's just 2, okay? Then shove all that in a formula, in which case we get the sum of the first 10 terms equals 3 times by 2 to the power of 10. So I've actually swapped this round and used the other one, okay? It really doesn't make much difference. It's entirely up to you. We've got 2 to the power of 10 minus 1 over 2 minus 1, and we can just pretty much shove that in a calculator and get 3069, okay? Right, this next one's where it gets a little bit more complicated. We're going to find the sum of the geometric series 1024 minus 500, blah, 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 all the way to 1. Right, there's an issue here, okay, and I'm going to show you where this would go wrong. Okay, so don't copy this, but this is just showing you where you might try and tackle this question, and thus why it would go wrong. So you know the first term, okay, you know the common ratio is minus a half, but it's the fact that this is minus that's going to cause us some problems, okay? So if you're doing questions like this yourself, you want to keep an eye out for when it's minus, okay? Right, we've got un equal to 1, and the reason I've done that is because if I know the last term, then I can work out, or I'm going to try and work out, but you're going to see this doesn't really work. You're going to try and work out how many terms there are based on the fact that we know the last term, okay? So we use our kind of general term formula thing, okay? 1 equals 1024 times by minus a half to the power of n minus 1, and we're just going to work that backwards to try and find out what n is. Okay, so we play around with it a bit. We get minus a half to the power of n minus 1 equals 1 over 1024. And then because they're both 1 over, we can just change them so that they're not. But the problem here is we're going to need to find n by finding the log of both sides, and we can't find the log of a negative. So this just isn't going to work. Okay, so yeah, kind of pointless me showing that, but you'd get to this stage if you were trying to do this yourself, because this is the method we kind of use for the arithmetic sequences. But it doesn't really work for the geometric ones. So it doesn't work when they're decreasing, in which case they have a negative ratio. So we have to take a different approach, okay? So we're just going to use our sum formula, knowing that the last term is 1, but we can rearrange this slightly, right? This version of the formula isn't given in a formula sheet, but it's a nice one if this circumstance arises. It's not always going to come up, okay? However, if you think about this, if you multiply this out, okay, and we're trying to basically make this ARN similar to AR to the power of n minus 1, because by doing that, then we find our term for UN, okay? That's just our general formula for UN. And once we've done that, then we can substitute it in instead of knowing what n is. So what we've done here is we've basically replaced it. So we don't need to know what n is. We just need to know what the last term is, or what our term in the sequence is, okay? Or more, we need to know the last term in the sequence. So if you memorize this version of the formula, okay, and you can get there by yourself by doing what I've just done there. All I've done is multiply out of the brackets, okay, and just try to introduce an AR to the power of n minus 1 by multiplying by r, okay? Then you can use that last term. It's a bit more complicated, okay, but it does work quite nicely for this situation. I'm not saying this situation is going to come up a lot, but when it does, you can't use the logs basically, because it's going to be a negative of a log, which we can't do. So nonetheless, when we work all that through, shove the numbers in, we get the sum of those terms is 683, okay? Right. For this one, find the smallest value of n such that the sum of 1 plus 2 plus a nice easy sequence there to n terms would exceed 1 million. Okay, so we had a similar one for the arithmetic ones. So we know the first term, we know the common ratio. Okay, we just don't know the how many terms we need, but we know that the sum of those terms needs to be greater than 1 million. Okay, so we need our formula to be greater than 1 million, and then we need to shove in our numbers and then basically work it back to find out n. Okay, but because it's to the power of n, we're going to need some logs at some point. Okay, so just simplify this down as much as we possibly can. You can multiply at the top, nice and easy. It's just 1 times by all, okay? And when we divide that by minus 1, this is where it might get a little bit more complicated, but you could just times both sides by minus 1, okay? But what I've done here is divided both parts by minus 1, because this is just the same as 1 over minus 1 minus 2 to the power of n over minus 1, which basically simplifies to minus 1 plus 2 to the power of n, or 2 to the power of n minus 1, okay? Which is greater than 1 million, and then if I add 1 to both sides, I get 2 to the power of n is greater than 1,000,001. And obviously I'm trying to find n, so I'll take the log of both sides so that I can bring the n down. N times by log of base e of 2 is greater than log of base e of 1,000,001, in which case I can divide both sides by log of base e of 2, and I can shove that in a calculator. N has to be greater than 19.93, in which case I need 20 terms. Okay. So a lot going on there. But nothing too unmanageable. This one is, again, a slightly different question. The sum of the first 3 terms of a geometric series is 23.75. If the first term is 5, find the possible values of r. So I don't know about you, but hopefully you've seen enough of these questions to know when it says something about possible values of r, it means there's lots of answers. And if there's lots of answers, this means it's probably going to be a quadratic, or maybe even, because we're advanced higher now, a cubic. Okay. Nonetheless, we have the first term is 5. We have the sum of 3 terms is 23.75. So we can pop this in our formula. 23.75 equals 5 times by 1 minus r cubed over 1 minus r. Okay. In which case, we can just play around with this a little bit. We're trying to find r. Okay. So we want to make this as nice as possible for ourselves. At the moment, we don't really like fractions, so multiply both sides and then multiply out. And as you can see, this gives us a cubic. So let's put it all to one side and simplify it as much as possible. We've got a common factor of 5 there, but we still need to take this 4r cubed minus 19r plus 15 equal to 0, and we need to solve it for r. Okay, if we're going to solve something like that, then we need synthetic division. Okay, so we've got our numbers across the top. Be very careful here. All these little things you're expected to know. If we're putting our numbers across the top, we have 4, we have 0, we have minus 19, and we have 15. Okay, so it's the coefficient of each of the terms, r cubed, r squared, r, and no r. Okay, so 4, 0, r squareds, minus 19, and 15. Right, from here it's a case of we need to obviously find a factor, okay? So you can put numbers in place of r. Because of those numbers, I'll be looking at 4, 19, and 15 and thinking, right, 1's probably going to work here, and it does. But however you choose to do it, I know where this answer goes to, and it's pretty horrific. You're going to have to find 1 because you're not going to find the other 2. But you need somewhere to start, the idea being if you've got somewhere to start, then you can find all the others by the quotient, okay? So synthetic division means we take the 4, we times it by the 1, and then we add on 0, and then we times it by 1, and then we add on minus 19, and then we times by 1. Yeah. Right, keep going until we get 0. That's what we wanted, but we kind of already, well, I would have checked this already in advance so that I don't have to keep doing this process. The main reason I want this process is to get my quotient numbers, get my 4, 4, and minus 15, okay? So I know when I basically divide this function by 1 minus r, or r minus 1, sorry, I'm left with 4r squared minus 4r minus 15, okay? So I've basically split it into 2 factors, but I can factorize it further because I've got a wee quadratic here. This is not the nicest of factorizations, but you're old enough and smart enough to be able to do this yourselves now. So 2r plus 5 and 2r minus 3 are our other 2 factors there, in which case we have solved this to give us r equal to 1 minus 5 over 2 and 3 over 2. However, this is not entirely finished because there's an issue with the fact that r is 1, or r could be 1, okay? Because if it's a geometric series, r cannot be 1, okay? If it was 1, then it would basically just be an arithmetic series, okay? Or it'd actually just be the same number again and again and again, okay? It wouldn't even be an arithmetic series. So we have to make that clear. R cannot equal 1, therefore the possible values are the other 2, minus 5 over 2 and 3 over 2, okay? So again, a lot going on in that question, but nothing you guys can't handle.